All right, hi everybody. Tonight we're going to talk about the periodic table and the atom. Much of this might be review for many of you, but most of us need the refresher on it. And then for some of you, we might be learning a little bit of new stuff as well. Give me just a second here. All right, so here's the periodic table. Why is this thing so important? You don't need to write this down. Let's just live it. Listen up. So it says it gives information on individual elements or atoms. It's a visual representation of the properties of elements. We're going to learn about that as we go. And it predicts, that's crazy, the existence and properties of elements yet to be discovered. It has been used over and over again to predict that this element or that element should exist, and then scientists go and find this or that element. So kind of cool. So what does what do each of the individual little rectangles tell us? Every periodic table is a little bit different. Some periodic tables have more, some have less information. And some of the numbers might be shifted around a little bit. But if you see a smaller whole number, that smaller whole number is going to tell you something different than the larger whole number. So this particular element is called selenium, and it's going to have an abbreviation. It's a capital letter. And if there's a second letter, it's going to be a lowercase letter. The atomic number is the smaller whole number, and then the mass number is the larger whole number. Some periodic tables, this number up here actually is a decimal, and we'll explain why that is. So not all periodic tables have it as a whole number. We'll explain that. All right, so what is an atom specifically? Well, remember, an atom is the smallest particle of an element that retains the properties of that element. There are particles that are smaller: protons, neutrons, electrons, and other things that we won't even discuss in this course are smaller than an atom. So what's so special about an atom? Well, an atom has everything necessary to have the properties of that particular element. Well, we'll just go with that. So it's got protons, neutrons, and electrons, and those are all part of it to make up one element. Please write this down. You probably should have written that definition down. And now please write this part down. What's inside of an atom? An atom has protons and neutrons that are contained in the nucleus. And so you can see the nucleus right here. And then it's got electrons that are orbiting on the outside. And when we're first learning, folks draw the orbiting electrons as though they're like planets orbiting the sun. And we're going to learn that that's a completely out of date analogy, that they really don't orbit like planets around the sun. But for learning purposes, it's good enough to say that the electrons are moving on the outside of the nucleus. Just a quick aside about the size: we cannot draw an atom to size correctly. The nucleus is so incredibly small on this diagram, you wouldn't even be able to see it. I've been told that a good analogy is a golf ball. That would be the size of the nucleus. Then if the nucleus was the size of the golf ball, the electrons are like a sports stadium, like a football stadium, traveling around the outside of the stadium, and this golf ball is in the middle of the stadium. The majority of an atom is empty space. There's a nucleus, and then super far away, orbiting around it, are these electrons. And again, they don't have a path just like a planet does, but we'll get to that. We'll learn a little bit more. Okay, and then I want you to add, where you've written protons, neutrons, electrons, and nucleus, nucleus shell, I want you to add their charges. So protons, remember, are positively charged. Neutrons are neutral. And then the one that maybe doesn't fit as well or is difficult to remember is electrons are the ones that are negatively charged. So the ones that are traveling on the outside are negatively charged. And here's another good image of it. Again, the nucleus, way too big. The nucleus should be so small that we wouldn't even be able to see it, and then the electrons are traveling on the outside. But for learning purposes, this is not drawn to scale so that we can see what's in the nucleus. If it's got pluses, those are protons. If it doesn't have anything, those are neutrons. And if it's got minuses, those are the electrons. All right, where did the wacky names that we see on the periodic table come from? They're named usually by the discoverer, although the name has to be approved by this ruling board of chemistry called IUPAC. Typically, they're named after people or places. So we have thorium is named after the god of thunder. Einsteinium, You can figure that one out. Berkelium is named after the place where it was discovered, University of California at Berkeley. And the symbol itself typically has one letter or two letters. If it's one letter, it's one capital letter. If it's two letters, it's a capital letter followed by a lowercase letter. You don't need to write this down. This is just pay attention and you're good enough. It's really, really important that when you're writing, if you're being sloppy and you make two things look like two capital letters or two lowercase letters, they will be marked wrong. And let me show you why. Cobalt is a capital C followed by a lowercase o. That's one element called cobalt. It's a pretty blue dye. Carbon monoxide is also C followed by an O, but notice this is a carbon and an oxygen, and that's a capital C and a capital O. And so if I can't tell the difference between your capital O and your lowercase o, then how am I supposed to know what you're trying to express to me? So very important that we have a capital letter followed by a lowercase letter. Sometimes the symbol is based off something unusual, which can be really frustrating. So like lead is Pb, and that has to do with the Latin root word for plumber called plumbus. Yeah, whatever. So anyway, some of them are kind of strange. Tungsten, the element tungsten, the letter for it, the symbol for it is the letter W. And that's because it's the element that's found in the mineral wolframite. I don't know why we couldn't just come up with a better like TU or something, but no, that's not what we do. We want it to be as difficult for learning students as possible. I didn't design it. All right, what do you need to know about atoms? You're going to write down three things here. The first thing is the atomic number. So we already saw the atomic number on the card. We mentioned the atomic number is that number that's down in the bottom left-hand corner of that card. It might be in a different location on a different one, but it represents the number of protons in one atom. So write that down. And I would like you to add that the number of protons determines which element it is. So if it has one proton, it's automatically hydrogen. If it has two protons, it's automatically helium. If it has six protons, it's automatically carbon. The number of electrons and neutrons might change. But if it has six protons, it's automatically carbon. So maybe write that as a little aside to yourself. Okay, so under normal conditions, almost by definition, protons, the number of positive charges, equals the number of negative charges or electrons. That's what an atom is. So if you have six protons, you're going to have six electrons if it's an atom. If for some reason you have more protons or more electrons, we now refer to that atom as an ion. And we'll learn about ions a little bit later. So today, and for your learning right now, protons equals electrons. But coming up soon, that won't be the case. All right, and then the periodic table is organized by the atomic number. So it starts with number 1, goes to number 2, 3, 4, 5. As you go across, you can tell that it's organized by the atomic number. So the more protons we have, the further down into the bottom right-hand corner it is. All right, please write down mass number. So in an atom, there are two particles that have mass, the protons and the neutrons. And we say they each have a mass of 1 atomic mass unit. So that's like saying they have a mass of 1 pound or 1 gram. They both equal the same, and it's 1. Each type of particle has a mass of 1. But we say that electrons have a negligible mass. We kind of ignore the mass. It's real. They do have a mass, and in some chemistry levels much further beyond this level, you do need to pay attention to the mass of the electron. But at this point, we don't care about the mass of the electron. So let me give you an example. Weight and mass are not quite the same thing. Remember that weight is determined by gravity. So if we have an astronaut standing on a scale here on Earth, that astronaut is going to have a certain weight. If we then place that astronaut and the scale into outer space, well, they're not going to have a weight on that scale because they're not even going to push down on the scale. They're both going to be floating around and there will be no weight. They're weightless in space. But the mass of that astronaut Hasn't changed. They have the same amount of matter when they were standing on Earth as they do when they're floating in outer space. So mass is how much matter they have. Okay, so the mass number is the amount of matter. And we say that protons and neutrons have the same amount of mass. And we say that electrons are negligible. Now I go like this for a reason. I'm drawing an analogy. It's not perfect. But imagine that I step on a scale. Now this is weight and not mass, but I'm making a point. If I step on a scale, my scale is going to register however much I weigh. And if I have dust on my shoulder, does the dust on my shoulder make my weight a little bit more? Sure it does. If my scale is really, really sensitive. But my scale is not that sensitive. So it doesn't even register the fact that I have dust on my shoulder. That's kind of like the mass number for an atom. The proton, the neutron, they both have a mass of 1, and electrons, their mass is so little that we just pretend that it doesn't have any mass. Okay, so mass number represents the mass of one atom, and it's calculated by writing or by adding protons plus neutrons. So I always tell students under mass number, just write protons plus neutrons, and you get to ignore the electrons. So why isn't the value shown on the periodic table a whole number? Most of the time, for example, carbon is listed as 12.011. If it's just the number of protons, 6, plus the number of neutrons, 6, 7, 8, it should be a whole number. Why isn't it a whole number? Well, we're going to get to that right now. All right, the next thing that you need to know, please write it down, is the average atomic mass. The average atomic mass is an average mass of all of the isotopes of the element. Write it down, and I'll explain what an isotope is. An isotope is an atom that has different numbers of neutrons. So remember, the protons of a particular element always have to be the same. So for it to be carbon, it has to have 6 protons. But the number of electrons could shift, and the number of neutrons that it has might be slightly different than and a different atom of or a different isotope of carbon might have different numbers of neutrons. So you might have one isotope of carbon that has 6 neutrons, and you might have one isotope of carbon that has 7 neutrons, and you might have one isotope of carbon that has 8 neutrons. That doesn't affect that it's carbon. Carbon always has 6 protons, number of neutrons shifts. Okay, so let's take a look at this card here. They didn't give you the average atomic number, they gave you the mass number. So it's a whole number, it's not an average. So we should be able to figure some stuff out. So first of all, it's gold. Of course, it's one of the dumb ones that has a weird symbol, so AU. So how many protons, neutrons, and electrons are in this particular atom or isotope of gold? Well, we know the 79 is the atomic number. So the atomic number tells us that there are 79 protons. If there are 79 protons, and this is an atom and not an ion, then the number of electrons is equal. So then it would have 79 electrons. But now we need to figure out the number of neutrons, and we do that with the mass number. The mass number is the protons plus the neutrons. So if we want to figure out how many neutrons there are, we do the mass number minus the protons to get the neutrons. So here we did 197 minus 79 to get 118. That's how many neutrons are in this atom of gold, this isotope of gold. I'm going to skip this slide. We don't need it. All right, valence electrons. Please write this word down. We're going to learn lots more about valence electrons. This is just your introduction to valence electrons. So valence electrons are the electrons found in the outermost shell. So imagine, this is an analogy because it's not accurate, but imagine our solar system and how Mercury is closer to the sun than, say, Neptune is. Neptune would be an example of a valence electron. It's the furthest away from the sun, whereas Mercury is a really close inner orbital. So then there's some rules about how many electrons can be in each of these, what we call shells or orbitals around the nucleus. So 2 rules, write them down. The first shell can hold 2 electrons. And the second, third, and fourth shells can hold 8 electrons. Now that is a very early on teaching you, because you're a beginner, rule, and we'll get a lot more detail as we go, and we'll change that rule a little bit. This model, this drawing here that you've probably seen before, is called the Bohr model of the atom. Bohr was a scientist that lived a few hundred years ago, and he was the first one that comes up really with the model of the atom. And now we've since improved on that model, but it's a great place for learners to start. Okay, so let's just practice this quickly. A review question. Atoms are they mostly positive or negative? Nope, they should be neutral if they're atoms. We're going to call them ions if they have a charge. Are they solid spheres or are they empty space? Remember, the nucleus is like a golf ball and the electrons are way far away, like the size of a football stadium. So the right answer is D, mostly space. From the textbook, you don't need to know this part, so I'm just going to skip ahead, but whose work led to the modern atomic theory? So we really kind of improved the model then, and that was Dalton, a scientist whose name is Dalton. All right, what are the two fundamental subatomic particles found in the nucleus? Look at your notes, see if you can find it. Protons and neutrons are found in the nucleus. Each of those has a mass of 1. You add them up to get the total mass. Now, take a look at this card. This card, notice that this time the atomic number is on top. So it's arranged differently on different periodic tables. And down here, this is the average atomic mass. It's got a decimal. That's not protons plus neutrons. There's something more going on, and we're going to figure that out. So first we have to learn what an isotope is. Please write the word isotope, and then let's write this definition. Isotopes are atoms with the same number of protons. So they're the same element because they have the same number of protons. So carbon always has 6 protons, but they have different numbers of neutrons. So they are atoms with the same number of protons, but different numbers of neutrons. And they're used for lots of things. Sometimes they're just, part of nature, but sometimes we use them for things like radioisotope dating to figure out how old something is. We use them for nuclear power, radioisotopes, smoke detectors. There's lots of other uses for radioisotopes. Okay, so now let's get into a little bit more about where the average atomic mass, why is this a decimal? If it's just protons plus neutrons, that should be a whole number, but it's an average. How do you calculate that average? It's actually called a weighted average. So one more time, the mass number is the sum of the protons and neutrons in the nucleus. So take a look at this diagram. We've got a carbon atom. It has 6 protons. It has 6 neutrons. So we say its mass number is 12. That's a whole number. That's really easy. So then it says the average atomic mass. We often just say atomic mass. We don't even say the word average in front of it. Oh, and by the way, I underline the A's. If you say atomic mass, not mass number, but atomic mass, I want you to think average. So there's the mass number. That's just protons plus neutrons, and it's a whole number. The atomic mass is the average mass. It does have decimals because it's a weighted average. So it's not going to be just protons plus neutrons. And I'm going to show you how to weight that average. Okay, so the average atomic mass of an element is the weighted average mass of the isotopes of that element. How you calculate it, we're going to learn how to calculate it, and you need to be able to do it on our test. So we'll be practicing this. So it says multiply. I'm reading right here. What happened? There we go. Multiply each isotope's mass by its percent frequency in decimal form, then add them together. Ooh, that was hard for me to read for some reason. All right, let's try it. So in this diagram, we have the isotopes carbon-12 and carbon-13. The 12 means the mass number is 12. So because it's carbon, it's got 6 protons. And to have a mass of 12, it must also have 6 neutrons. That's what carbon-12 is, and it's a whole number. 6 protons plus 6 neutrons equals 12. Easy peasy. Carbon-13 is an isotope of carbon, and here we're saying it makes up the other 1% of carbon. 99% is carbon-12. There is also carbon-14, and it's something like 0.00 some odd weird number percent. So we ignore it for this example problem. So carbon 13, the 13 is its mass, and that means because it's carbon, it has 6 protons, but this one has 7 neutrons. That's why we have a mass of 13. So carbon 12 is a whole number, carbon 13 is a whole number. Why is the average atomic mass 12.01? Well, that's because it's an average, and it's a weighted average, and that means it depends what percent of each atom is carbon 12 or carbon 13. So in our equation, 99% of carbon is 12 and 1% is carbon 13. So this is how you do the math. You take the mass number 12 and multiply it by the percent in decimal form. We call that frequency. So instead of by 99, you multiply it by 0.99. Put that in parentheses, 12 times 0.99. Then you add it to the next isotope, which was 13, had a mass of 13, times, and then 1% in decimal form is 0.01. Close parentheses, add that together, and it makes sense, right? That if there are carbons that have 12 and there are carbons that have 13 for the mass, that the overall mass would be slightly higher than 12. But it's barely higher than 12 because carbon 13 only makes up 1% of the carbon in the universe. And so it's a little bit above 12, but not by much. All right, let's just practice a couple review questions and then we're all done. Elements with the same number of protons and differing number of neutrons are known as isotopes. Those are isotopes. Same number of protons means they're the same element, but number of protons changes their mass, and so that's an isotope. And then this one's a little bit tricky. An unknown element has 19 protons. So if it's unknown, all you have to do is walk over to a periodic table and look for the one that's number 19. If it's got 19 protons, then you know what element it is. It also has 19 electrons, so that's important because the protons and electrons are equal. So we call that an atom and not an ion. It doesn't have a charge. And it has 3 isotopes with 20, 21, and 22 neutrons. So to calculate the mass of each one, we would have to do the protons plus the neutrons. So we would say 19 plus 20, and we'd have a mass of 39, a mass number of 39 for that isotope. Or 19 plus 21, the mass number would be, I can't do it very quickly, it would be 40. Did I do it right? 39 was the other one. 39 was the first one. 40 is the second one. And 41 is the third one. My brain, it's too hard. Anyway, so those are the mass numbers. Now, if we wanted to calculate the atomic mass, that's not what they're asking here. They're asking for atomic number. But if we wanted to calculate the atomic mass, remember that's the average atomic mass. In order to do that, we would need to know what percent of the isotopes are at this mass, what percent of the isotopes have this mass, and what percent of the isotopes have this mass. They didn't give us that in this information, so we can't calculate the average atomic mass. However, we can figure out what the atomic number is. The atomic number is the number of protons. So they told us 19 protons, so 19 is the correct answer. All right, everybody, that's it. We will continue learning about atoms and the periodic table very soon. Have a good day. Bye-bye.